Okay, so in the third and final question, we need to find out the marginal function of x and y, and we also need to draw it and prove that they are valid density functions. Well, in order to find the marginal function of fx, the first and foremost thing is very easy. Just go with the definition. And that part is pretty easy. We just need to integrate y and y only of the joint function that are given in the problem. So we substitute this like this. I wrote dy means the area, the projection of the dy onto the y-axis, So like this one. So the integration should be like this. However, when we want to find out the marginal function of fx, we should do the integration of dy. But we come across a major problem. As you can see, the area, when we project it on the y-axis, there's some overlap. I mean, the left part, if we project it on the left part, it's like from infinity. Seems like from infinity to 1. However, if we want to project the right part, both the right and left part are divided by the vertical line x equals to 1. And it seems that the projection, it seems that the projection is also the area from 1 to infinity. So that's actually why we cannot integrate y in the first place. We integrated x in the first place in our previous questions, but now we have no choice. I mean, we must integrate x in the first place. We need to find out a way to resolve this. Well, the only way is to discuss separately. We divided x into two parts. One is x is less than 1. The other is x is bigger than 1. Well, such methods are not so difficult to become out because in double integrals or we have to integrate over a surface, and when we project the surface onto Descartes' coordinates, it often happens when there is overlap. So in that case, we just need to cut the surface into several pieces, and that then adds the final result together. So similar to that, acting to that, we could treat this in a similar way. So we first need to deal with the situation when x is less than 1. So y, it's from, and we couldn't say it's from 1 to infinity because y is actually bounded by the curve, in this case the hyperbola. It's y equals 1 over x, so it's actually 1 over x to infinity, and the upper limit should be infinity. And like, we need to stress that we are limiting x is in the situation where x is smaller than 1. So we add a step function to illustrate that. And also similarly, we could write the same. So x in this part, y is equal to x. So x to infinity, 2 minus 1. X minus 1. Such things could be written in the integral outside integral anyway. We're gonna not do integration to that anyway, so it doesn't really matter. When we integrate that, we could finally get an answer of that, like 1. Well, I'm going to omit the concrete calculations because there's nothing new about it. uy minus 1 equals plus 1 over s squared u x minus 1. So we're gonna, so actually in this part, there's also parentheses. So actually in this part, we use a generalized function to express the form of fx, the density function of x. Okay, next we're gonna draw it. Okay, then knowing that we need to draw it. Well, in order to draw it, it's how well we just simply divide the graph into two parts. The first part when x is smaller than 1, however, x must be larger than 0. This is held obvious. And this is actually a uniform distribution. By uniform distribution, y it's just like a constant signal. So we could simply draw it here. So when x is between 0 and 1, it's like a constant signal only with the height of 1/2. This is a little bit out of scale. However, when x it's larger than 1, this is actually 1/cubic x, and it should be the inverse function of the cubic function. But we know that there is a jump, and it should like fall right. When x goes to infinity, this goes to 0. So it will be sort of like that. So the overall function is a bit like that. As for proof of its validity, we could just simply, we could do the integration here. Just integrate this from 0 to infinity, and well, the calculations, simply saying, we could divide the calculation into two parts, from 0 to 1, in which case this holds 1, this is 0, and from 1 to infinity. And our final result is that we actually could get that easily. So because in 0 to 1, this is just 1/2. And for that, we get like that. Oh, so this is we could easily get that too. So basically, we could verify that this is a valid density function.